Welcome back to another AP Pre-Calc video. I'm Mr. Hibble. Today we're looking at our 3.12 notes. This note section today is all about secant and cosecant graphs. Well, because secant and cosecant are based off of sine and cosine, right? They're the reciprocals of sine and cosine. The graphs are similar to how a reciprocal is found, right? A reciprocal is the flipped fraction. Well, the graphs are basically just the flipped version of those graphs as well. So one thing you might do when you're creating these graphs is start by sketching the reciprocal. For example, on this one, we want to graph cosecant. So I might start by first graphing 3 sine of 2 pi x. Okay, well, if I'm looking for sine, what we know about sine is it starts at the midline. In this case, we have an amplitude of 3, so our graph's going to go up to here and down to maybe here. You can always find the period by taking 2 pi over the b value. In this case, our b value is 2 pi as well. So the period is 1. So what that tells me is, okay, our graph should go all the way up to 3. It should go back down to the midline at halfway and go down and return to 1 to complete its period. We might also do that on this other side, getting a quick sketch on that side. We should have something that looks like this. Okay, it's a sketch, right? It's not perfect. It's a little shaky for some reason, but that's okay, right? It's a sketch. It gives us the right idea. Well, realize if you're finding the reciprocal of some of these values, for example, if I'm finding the reciprocal right here at 1/2, well, let's see what that would look like. Let's just first find the sine value. Well, we know because we're at the x-intercept there, if I were to plug in the x value of 1/2, we would get sine of pi. We know sine of pi is equal to 0, so 0 times 3 just gives us 0. Well, think about taking the reciprocal of 0. The reciprocal of that then is 1 over 0. And what this tells us is anytime there's an x-intercept for sine or cosine, what's going to happen is when you take the reciprocal, you're going to get an undefined value. Well, where the function is undefined, that actually is where the asymptotes will occur. In this case, we're going to have a vertical asymptote going up and down for the cosecant graph. So, okay, we can sketch those asymptotes at every single x-intercept. Okay, speeding it up. Now it looks something like this. But again, when you are taking a reciprocal, you're really just flipping it. So what's going to happen is at any of these coordinates, for example, if I'm at the coordinate up here, then what I can do is I can just flip this graph. But because there's asymptotes, your graph is just going to go alongside it. It's going to get infinitely close to it, but never actually cross it. So all we're doing now is just flipping each one of these graphs to now go in the other direction. There is our sketch. There is our graph for cosecant. Realize the cosecant graph is the blue one. Okay, the purple one was sine, blue is cosecant. There's your sketch. Same idea for secant, right? You can do the exact same process. You can find the amplitude. You can sketch that. Oops, negative 1/3. We can figure out the period. The period in this case is just going to be 2 pi because the b value is 1. So, okay, it goes over to here and to negative 2 pi. And we know secant is the reciprocal of cosine. So I'm going to start by sketching my cosine function, and then once we do that, we can sketch secant. Something like that. Same idea on this other side. Something like that. Again, it's a sketch. It's not perfect. Maybe if you have grid or something, it might be better. We sketch cosine. Anywhere it crosses the x-axis, you'd have a value of 0. The reciprocal of 0 would make these values undefined. We showed that process earlier. So here's the asymptotes for the secant function now. And now just start to flip each of these sections. We flip them. We flip them. This part's just flipping that side. It would continue over there as well, notice. And now you have your rough sketch of these U shapes and what it would look like for secant. So graphing it shouldn't be too bad. Find the period, find the amplitude. If there is a horizontal shift, you might have to take these values now, these x-intercepts, and move them in some direction. But this is the general idea. Another thing we can do, though, is we might be given functions and have to determine some of the key features. And yes, you could find these features by graphing it, but we know we can also recognize each of these values by analyzing the function itself. For example, the period we know is 2 pi over the b value, so 2 pi over 1/2, which is 4 pi. We can also identify the horizontal shift, the vertical shift. We'll look at domain and range, which are slightly more complicated. The horizontal shift, okay, well, that would be on the inside. It looks like it's plus, so it's going to the left, pi halves. The 8 on the outside is our vertical shift. That's moving it up 8 units. Right? We have these transformations down pretty well. Domain. Well, think about the domain of each of these functions. The domain for cosine and sine is all real numbers. Well, these functions, secant and cosecant, have the same domain except for one difference. The difference is that at every x-intercept for sine or cosine, there is an asymptote. So we have to exclude those values from the domain. But again, we can start by saying it is all real numbers. But x cannot be equal to a few things, to the asymptotes. Well, how can we find the asymptotes? We said the asymptotes occur when sine or cosine is equal to 0. Realize I'm looking at domain, so I don't care about the 8 or the 5, as those changes affect the y values. They affect the range. So now I'm just solving this equation. Well, we know that we need an angle because on the inside here is the x. Whatever's inside sine or cosine, that's an angle. So I need some angle that causes sine to have a value of 0. Well, if you think about the unit circle, if you look at the unit circle, that angle that would cause that is 0 degrees or 0 radians. So what we can do is say 0 equals the inside. It's equal to the angle that's on the inside. So now we can start to solve. I can move the 1/2 over, but multiplying by 2 gets rid of that as it's just multiplying with 0. We can subtract the 1/2 over, and we find that there is an asymptote at x equals negative pi halves. But when we look at functions like cosecant, it's not just one asymptote. These asymptotes occur all the time. We'll realize how often they actually occur. If we look at this span here of one period, we notice that there is an asymptote in the middle of the period. It's halfway between the period. So what we could do is we could end up taking the asymptote we have found and we could add it with half the period. What is half the period? Well, half the period would be 4 pi divided by 2, which is 2 pi. In this case, with the function we are looking at, there is an asymptote at negative pi halves in every other 2 pi after that or before that. So we put the letter k where k is some integer. Now we have found the domain. Realize for cosecant, one thing I do want to point out, when there is no horizontal shift, no phase shift, that means there's an asymptote at 0. If there is a phase shift for cosecant, it just takes the asymptote from 0 and it shifts it. Notice where the asymptote was. We had a horizontal shift of left pi halves. That made the asymptote at negative pi halves. Let's look at the range. Range, if we look at this graph, we know it goes down forever with those arrows. It goes up forever. But we exclude this area in the middle. Well, we can find those values by figuring out the minimum of our sine or cosine graph as well as the maximum of our sine or cosine graph. We know that those are where the function for cosecant and secant would stop. Well, in this case, we have a midline of 8 for our function. We have an amplitude of 5. So I know that the minimum is a value of 3. I know that the maximum is a value of 13. So let's develop the range. The function goes down forever. It would stop at 3. It would re-pick up at 13 and go forever. Realize 3 and 13 are included. Those would be actual values for this function. We have gone through that problem. Let's look at another one real quick. Let's look at E. Same idea, but now for a secant function. Again, the different parts. The period should be quick, but wait, notice the inside. The inside is not in factored form, so make sure you divide the 3 out so it is in factored form. Find the period, 2 pi over the b value. We've found it. Realize we did also want half the period. That means that if I multiply this by 1/2, I would get half the period, which looks like pi thirds then. The horizontal shift is quick now that it's in factored form. This one would be going left pi. Looks like I made a mistake on that last one. It should have been, no, the last one was fine. This one I just made a mistake on. Mixing up my lefts and rights. That's unbelievable. This one is going right pi. Okay, right. Yep, that's good now. So right pi units. The vertical shift is going down 2. And now let's talk about the complicated parts, the domain and the range. Domain for secant does not have any shortcuts like it did for cosecant, right? Cosecant, we could just take the phase shift or the horizontal shift, and that's where an asymptote would be. Secant, when we look at a secant graph, it's not the same, right? You need to figure out where cosine is equal to 0 for that, and that doesn't just occur at 0 normally. So we need to solve this function. We could take, again, cosine, set it equal to 0. You can ignore the changes that affect the y direction. And we just need to solve this. We need an angle that causes cosine to equal 0. Cosine is equal to 0 at pi halves. Start to solve. Divide the 3 over. Add the pi over. And you end up finding that there's an asymptote at 7 pi over 6. So our domain is all real numbers, but we need to exclude the asymptotes. So we exclude 7 pi 6, and these asymptotes occur every half period. So I add it with pi thirds k. Again, k is some integer. The range, the very last step, find the maximum, find the minimum. Our midline is -2. We go up 2, we go down 2. So the maximum is 0, the minimum is -4, and now we know the range. Let's go ahead and look at one more problem. This one says determine the equation of the graph. Well, a few things we need to understand is whether we have a secant graph or a cosecant graph. You could use either if you want to apply a horizontal shift, but realize we know cosine. Cosine starts at the maximum on the y-axis. Well, in this case, this function is on the y-axis and at that maximum where the cosine function would be. So in this case, we can use a secant graph. So, okay, one thing we're going to need is just the different changes. You might find the midline. You might figure out what the period is for this function. So we know it's secant. Well, okay, one thing I'm noticing is we go from maximum to maximum for our cosine graph in a timeline of 4 units here. So it looks like the period is 4. So if I need to find our b value, it would be 2 pi over 4, which is pi halves. There is no horizontal shift, so there's nothing else that I need on the inside of this function. Notice they do say k of w. I'm going to change that to a w instead. Okay, but besides that, then we need to find other things. Well, this function has a midline at -2, so it got shifted down 2 units. It also has an amplitude of 3, so we need to make sure we apply that at the beginning. Well, okay, we have each of our different parts now. Now we have the equation of this function. Thank you for watching. Come back next time.